Welcome to this explainer. Look, if you're making the call on hardware strategy or managing heavy-duty tech budgets, you already know we're way past just looking at wires and silicon. Today, we're doing a high-level briefing on how foundational integrated circuit technologies actually drive quantifiable business outcomes. We're talking cost savings, production yields, and space efficiency. Understanding the base architecture of these chips isn't just for the engineers, it's absolutely essential for the bottom line. So, here's our roadmap for today. First, we'll hit the economics of integration. Then we'll trace the manufacturing value chain, look at packaging and space efficiency, and finally wrap up with core logic and memory capabilities. Let's dive right in.
All right, part 1, the economics of integration.
We really need to anchor our strategy on this core insight from the source material. It plainly states that considerable cost savings can be made by manufacturing all components on one small slice of semiconductor material. Miniaturization isn't just some fascinating engineering feat, right? It is fundamentally a cost-saving business strategy. Every single transistor we can pack onto a chip is a discrete component we don't have to individually manufacture, ship, or solder. To put some numbers to that technological leverage, think about this scale. We're jumping from small-scale integration, maybe 1 to 10 logic gates, all the way up to ultra-large-scale integration, boasting well over 100,000 gates. It gives us a really clear metric for the exponential leap in computing density. I mean, moving from basic logic to massive microprocessors completely rewrites the economic profile of what a single piece of hardware can actually accomplish. Now, to give you a quick mental map of what we're actually integrating into these products, we can bucket the technology supply chain into 3 main pillars. We've got digital for processing, so your logic gates and microprocessors. Then there's analog for linear operations like amplifiers and regulators. And finally, hybrid, which bridges the gap using analog to digital and digital to analog converters. Pinning down these categories really helps map out exactly where your component dependencies lie. Moving right along to part 2, the manufacturing value chain. This is where it all starts. Our manufacturing canvas. A single 30-centimeter pure silicon wafer is capable of holding thousands of these highly dense, cost-saving components. This one disk represents the incredible economy of scale that makes modern electronics even viable. It literally turns a simple slice of silicon into massive, scalable computing power. If we distill this incredibly complex manufacturing process down to 4 key stages, it goes like this. First, growing the pure crystal. Second, the incredibly precise photolithographic etching of the circuits using ultraviolet light. Third, cutting the wafer into individual rectangular die. And finally, the vital testing phase. It's honestly a marvel of modern manufacturing. But here's the absolute kicker, the financial bottleneck right at the end of that pipeline. As we scale up to those massive, very large and ultra-large chips, testing accounts for a huge proportion of the production cost, and yields can drop dramatically. Quality assurance isn't just a technical hoop to jump through anymore, it becomes a massive line item that can totally make or break a product's profitability. Okay, let's get into part 3, packaging and space efficiency. Hardware real estate changes incredibly fast. Just think about the shift from those older, bulky dual-in-line packages to the highly dense, surface-mounted plastic quad flat packages. In hardware development, physical space is money. Transitioning from through-hole mounting to surface mounting was a total revolution in how we size our products. Because as processing power just exploded, chips blew right past the practical 68-pin limit of that older packaging. The business drive for space efficiency basically forced the rapid adoption of solutions like quad flat and thin small outline packages. These let us pack several hundred pins into a fraction of the space. It keeps high connectivity without forcing the final product to be, the size of a suitcase. Finally, part 4, core logic and memory capabilities. Look, as strategic leaders, we don't need to be down in the weeds soldering these things, but we absolutely must grasp the fundamentals. Take flip-flops, for example. They serve as the foundational storage blocks for all memory operations. They are essentially bistable circuits that hold a state, storing a bit of data. They're the literal bedrock of our digital memory. But there's a pretty massive operational risk with basic RS flip-flops. In their logic truth table, there's a disallowed state. If both inputs happen to receive a signal at the exact same time, the circuit enters an unpredictable logic error. And let's be real, in mission-critical enterprise hardware, an unpredictable error state is a massive liability. You just can't have it. So, to fix that error rate and lock down system stability, the industry pivoted to the JK flip-flop.
It has the distinct advantage of completely eliminating those disallowed error states. By guaranteeing reliability and accuracy in logic execution, upgrading this component directly translates to less downtime and far higher reliability in your finished product. It's a real game changer.
Another totally essential capability relies on comparators. Think of these as our built-in automated quality control at the micro level. They compare sets of binary numbers to act as parity checkers, instantly flagging if a data set is greater than, less than, or equal to another. They are what ensures our system's accuracy at lightning speeds.
And since real-world data sets are massive, components like the 4-bit 7485 chip are built to be cascaded. We can just link these specific chips together, comparing units, then tens, then hundreds. It sequentially expands our capacity to compare larger and larger data sets flawlessly, without skipping a beat.
So I want to leave you with a thought for your own hardware strategy. The capability of these components is staggering, no doubt about it, but it comes at a price. How are we balancing the relentless race for smaller, denser chips against the very real rising budget constraints of stringent testing and yield losses? Because the leaders who can strike the right balance between maximum integration and solid manufacturing economics are for sure the ones who will dominate the market. Thanks for joining me on this explainer, and I hope this gives you a much clearer lens for your next big technology roadmap.